Heyo and welcome back. Today we're going to be talking about a technique that's the favorite of hackers worldwide, and that is the Buffer Overflow Attack. We'll get into what it is, how it works to hack computer systems, including some techniques you can use to prevent it. As always, a big shout out and thank you to our patron Ian, as well as our returning subscribers, of which we have a few more than that already. We couldn't do this without your continued support and interest. If you want to continue to see more of this type of content, consider supporting us with your likes, subs, and comments down below. Also, ring that bell so you never miss an episode as we once more take a dive into the deep end of computing with the Yup 5108 virtual microcontroller. Over the years, Hollywood has depicted hacking as a vibrant, dynamic, off-the-cuff kind of action, when in reality it is usually accomplished only after detailed system analysis, long before a hack is ever attempted. Unlike social engineering, where a hacker steals or tricks a trusted user into giving up their credentials or even finds a much-fabled backdoor into a secure system, a buffer overflow attack relies on a specific set of circumstances within the software of the login code. To demonstrate this, I've created a login program for the Yup 5108 that is pretty straightforward. It prints a boot banner, asks to get a PIN number, checks if the PIN is correct. In this case, it rejects all of them. And then if it's a bad PIN, it just asks over and over again. So if you do put in a good PIN, which for now will be impossible, as all logins will be rejected. As a quick review, we've got our label for our main, where we want to put that in our boot sector. I'm going to skip over the vectors and bring in an include file of boot banner prompts. And then the C code for this would be, in effect, character prompt bracket bracket equals enter pin. But what we're doing in assembly is we're going to create a label called prompt with an address in ROM, and then we're going to say stuff these bits, or bytes rather, into that address in ROM. And I've gone ahead and added a couple of features to the assembler, one of which is being able to take these sort of /0/n codes that are very typical in C, so that I don't have to put in the constants using the L command. So after that, we have our welcome string once you're granted access, which you should never be granted access with this code, which consists of creating a label. We clear the screen, then we say access granted, carriage return, welcome to the Yup admin mode. And then, of course, since we're asking for a PIN, we're going to get a PIN entered of 4 bytes long. We create an address in RAM to create a label for that address, and then add 4 bytes so that the next variable we create, even though we create none here, but the next variable we create would be spaced 4 away. And then we start loading up our actual executable code. So, as we mentioned before, different systems have different ways of locating their text section, the executable part of the code. We're going to put ours at 2000. And we're going to start by loading up all the I/O functions. Then we're going to do the equivalent of defining main in C. We create a label for main, the function name. Then we're going to do our print ROM of the boot banner, which amounts to loading the boot banner location into the DR register, and then calling the print ROM function since this boot banner is in ROM. And we're going to do sort of a continuous loop. So we're going to say do, create a label for that so that we can come back to the top of this loop. We're going to print the ROM of the prompt string, which is enter a pin. So we load that address and call print ROM again. Then we do a get string into the variable pin entered. To do that, we load the address of pin entered, and we tell it to do get string. Once that returns, we'll print a carriage return, and then we're going to check if the pin that was entered is valid. And so this equivalent of this is that the variable in0 is equal to whatever is returned from check pin, and we pass in the pin that we're interested in. So again, we load up the address of the pin entered variable, call check pin function, and as long as there is something non-zero, we're going to jump back to the top of the do loop. And what that means is that the check pin function should look at the pin, see if it matches. If it doesn't match, return something other than 0. If it does match, return 0, or in this case, the flags the processor will have the non-zero flag set or not. But as you can see, our check pin function, defined down here with first a label, and then all we do in the check pin function is load a high value, or FF, into the B register, which sets the non-zero flag, and then we simply return. So no matter what we pass in as a pin entered, we always return as a failure. So let's take a look at this. We've got it already loaded up in Logisim. We're going to look at it from this view, where we can take a look at the registers while we go. Light it up. Make sure the keyboard's active. There we go. And now let's enter a pin. 1, 2, 3, 4. Nope. How about 5108? Nope. How about 4567? Nope. None of those work. But if you take a look here, our stack pointer, which includes the 2 bytes that tell us where to return to, meaning the return address is at FE and FF, whereas our data pointer is at F0. So if we just put in the right number of characters, let's start, the difference between FD and F0 is 14, so we'll put in 14 meaningless characters at this point. Let's just do U, W, E, R, T, Y, U, I, O, D, A, S, D, F. So now what you'll notice is that our data pointer is now pointing at FE. So the next 2 bytes we put in here will overwrite the return address on the stack. So what 2 bytes do we want? Let's take a look over at our source files. And as you can see, we now have the map file and the symbol table are separate files that are output after compilation, or assembly rather. So if we look at this, we see that right after the jump back for main.do, the do loop, we do this instruction, which is located at address 2054. Now, due to the nature of a returning from a function call, we add 3 to the returned address to skip over the original call and address, which means that what we want to put in here is 2051 in hexadecimal. And 2051 in hexadecimal happens to be space and capital Q. So now, as you can see, our data pointer has gone all the way past memory and gone back around to 0. And when we hit enter to return from this function, we're going to return past the check on whether this is a valid pin and just get immediate access. So that's the basics of a Stack Overflow hack. So how did we know what address to put in? It came from our compiler's or assembler's map file, which is because we're effectively open source. So am I saying that open source code such as Linux is inherently less secure than a co-source alternative? Not directly. If this were a PC or some other system that executed code out of RAM instead of out of ROM, we could have used those first 14 characters of the buffer overflow to be other instructions and actually run arbitrary code on the machine. In this case, with our design, you can only change what code is run next in the ROM using this kind of buffer overflow attack. The reason the YUP 5108 only runs out of ROM is because the instruction register is only loaded directly from the ROM chip instead of off the bus in general. Although you can write to the ROM using these instructions in the YUP instruction set, I've added a write enable line kill switch to the ROM, which defaults to off. So, in other words, your program could run, but it wouldn't actually write to ROM because we've circumvented the ability to enable writes to the ROM chip itself. In some microcontrollers, this switch is actually a fuse, and by applying the correct voltage, usually higher than normal voltage, you burn out the fuse and therefore make permanent the contents of the ROM at that time. But luckily, there are a number of ways in which we can mitigate issues due to buffer overflow The primary prevention would come from security-minded coding, which would include passing pointers to global or module level variables rather than local variables that are stored on the stack, not using any of the unbounded string functions such as string copy, string cat, string compare, and instead use their bounded versions, string incopy, string incompare, etc. Also, do not allow extra characters to be entered. In our example, we asked for a pin, which would have implied digits only, but allowed them to enter any character whatsoever, including the space in the queue. Had we rejected those characters as not being digits, the ability to execute a buffer overflow attack would be greatly diminished. Of course, this is a discussion about hacking a system remotely or through its designed interface. Having a target system in the lab that you can open up and probe, modify, reprogram is really a different matter altogether. So that's pretty much what I had for today's video. I hope you enjoyed it. Be sure to check out the full Yup 5108 series playlist, and we'll see you next time. Hey, and welcome back. Today we're going to start this over again because I already forgot my mic. Be sure to check out the Today we're going to be talking about the... This is a sound test now.